Well, thanks very much, everyone, for coming for lunch today. So, indeed, the title of my talk is Generalizing the Standard Model. As you probably guessed, this is a slight play on words. So, there's sort of two things that will be themes of the talk. One is, indeed, as Lars advertised, this talk is in some sense about some of what has been going on in the What is Particle Theory program. I'll say a bit about that, more about that in a second. So of course, part of the endeavor of particle theory, part of the what that particle theory is trying to do, is to take this beautiful framework that we have, the standard model of particle physics, and to understand what is the microscopic theory that underlies it, and that in that sense that amounts to generalizing the standard model. Of course, you know, not coincidentally, because there is a program that has now started at KITP on generalized symmetries, there's another more specific meaning to this talk, which is trying to build relations between the generalized symmetries program, the standard model, and physics beyond the standard model, and that will be sort of the focus of the second half of my talk today. Before I get into this, I just want to say something briefly about the program that this is a Blackboard Talk for. So what is particle theory? It's been fun. We're in week 11 of this program, and you know, for the first 10 weeks, it's been fun to listen to participants in other programs speculate as to what this actually means. I believe early on in our program, someone in another program said, well, I guess they have to figure out what it is they're going to do so they can do it. But really where this title comes from, as many of you know, there was a beautiful set of Les lectures given by KITP's Joe Polchinski in 1994 that were called What is String Theory? And these lectures he gave, it was really on the cusp of the second string revolution. And so in these lectures, of course, he was articulating the perturbative understanding of string theory that existed until that point, and then laying out the case for the understanding of the non-perturbative object. And of course, as we know, the understanding of those non-perturbative objects gave rise to the second string revolution and all of the amazing physics that followed. And so, in fact, there was a program at KITP last year, as Lars alluded, called What is String Theory, which was in some sense following up on Polchinski's original vision. But also just connecting the string theory community in the decades that had followed. And so the What is Particle Theory program really also kind of has two parts in that same sense. One of them is, you know, we've been doing particle theory for a very long time, but a lot of what's been done, especially when you think about generalizing the standard model, is done in the framework of perturbation theory. And we're in a golden age of quantum field theory, where non-perturbative methods in 4 dimensions and diverse other dimensions have gotten quite advanced. And so there's a sense in which we can bring these non-perturbative methods to bear on many of the questions in particle theory. So one of the goals of the program was to do that, you know, in direct analogy with Joe's lectures, figure out what new methods in quantum field theory we could use to address the problems in particle physics. The other bit was sort of a more meta question. So as you can no doubt have noticed, I've drawn some scales at the top of the board, which, because I'm a little vertically challenged, I'm not going to get there with the rest of my lecture. But this is in some sense laying the set of scales over which, right, the story of particle theory unfolds. Here I've written, this is all in giga-electron volts. And so we're up here at 10 to the 18, 10 to the 19 GeV, where we expect the theory of quantum gravity takes hold, all the way down to 10 to the minus 30 giga-electron volts, which is sort of the lightest scales that can be populated by dark matter as we know it. And so, of course, anytime you're in a field that covers 50 orders of magnitude, there is a question about how you all stay in causal contact. But at the end of the day, we're all doing primarily quantum field theory in 3+1 dimensions. And so there's a sense in this program that we should take advantage of that to get people from different parts of the field to engage in dialogue and build up from the intersection of their expertise. Okay, so that's sort of the two goals of what is particle theory, and that's what we've been doing now for 11 weeks running. Okay. So today's talk, as you may know, does anyone know today's a special holiday? If you have children, you especially know because they've been pinching you. Right? Okay, so it's St. Patrick's Day. And so, of course, the sort of icon of St. Patrick is the shamrock, so the 3-leafed clover. And so in my talk today, I decided I'm going to have a theme of 3s. And so you'll see that over and over again. So I have 3 goals for the talk, and we'll see if I can get to them. One, of course, is the conventional goal of a Blackboard Talk, which is to give a sort of a summary or vision from the What is Particle Theory program out towards all of KITP. There's a second goal, which is somewhat more specific, because we're now operating in parallel with the Generalized Symmetries program, is to really build specific bridges between the Particle Theory program and the Generalized Symmetries program. It's also the second meaning of my talk title. And the third goal is within the What is Particle Theory program, the program runs for 14 weeks, for week 11, and we have kind of a ship of Theseus problem, right? So if you know the Theseus' paradox, Theseus has a ship. Over time, they have to replace each one of the parts. Once you replace all of the parts, is it really the same Theseus' ship? And that's just to say we've had so many people coming through the program, so many great ideas discussed. Many of the people who are here now weren't here when we started this program. And so I also just wanted to connect people who are newly arrived in the program to some of the developments that have happened earlier. All right, so the talk is going to go, again, in how many parts? How many parts should my talk be? 3. Okay, good. Justin's got it. So the first thing, I just want to survey a couple of open problems in particle theory. These are not new problems. These are old problems. But that's the point, because what we really need are new methods or even new ways of bringing old methods to bear on them to make progress. But I just want to set the stage with the open problems. I want to sketch 3 opportunities, which are things that have come up over the course of this program as opportunities that might be useful, haven't necessarily yet fully been brought to bear on all of the problems that cover this range of energies, but may well be. I should say we've covered an enormous amount of ground in the program, and so I had to sort of find some criteria to select the highlights I'm going to give you. So I'm not going to be able to touch on a fraction of the things we've done. The opportunities I'm going to tell you about, they all have something in common, which is that they were in some sense first developed actually in the context of trying to make sense of the theory of strong interactions 50 years ago. And either they continued to be applied in that context over the intervening years, or in fact they wandered off into more formal areas of quantum field theory or diverse dimensions. But now it's really an excellent time to bring them back and bring them to bear on the problems of particle theory. So the 3 opportunities I want to highlight. The other reason I've chosen these 3 is that solving the ship of Theseus problem. There have been some people, some miraculous people who have been at the program this entire time. And so I wanted to connect to some of the problems especially that they think about so you have an opportunity to engage in dialogue with them. So one of them is lattice gauge theory. Of course, this lattice gauge theory has been around and doing amazing work for decades, but the thing I want to highlight is the relevance to problems of particle physics that haven't necessarily been oriented towards lattice methods. And I just want to, in terms of people who have been around this entire time, who I'd encourage you to talk to for more detail about this, of course, my co-organizer, Aida Al-Qadra, and Anna Hassenfratz. And I want to spend a little bit of time today just highlighting some of the amazing things that Anna has to teach us, and we're going to build on that through the remainder of the program. The second thing I want to highlight is the S-matrix bootstrap, which again is something that has developed dramatically over the past decade, but I think we're only now beginning to realize how we might put it to work for the problems of particle physics. And again, there's a number of wonderful people here who you should talk to about this. Just to name a few, Justin Berman, Brenda Bellazzini, and Alex Homrich. And I apologize if there's someone who's been here since week 1 who works on the S-matrix bootstrap and I haven't listed you. Feel free to speak up. And then the final one I want to mention somewhat briefly are energy correlators, which again have been around since the early days of QCD. Now they're being applied to great effect to QCD at colliders, but also I have a sense in which they are useful more broadly in terms of addressing questions in particle theory. And so people I would encourage you to talk to who have been around since the start of the program include Evan Kraft and Ian Molt. The one thing, of course, since my theme 6 me to 3, I had to drop a 4th, which in some sense is a talk of its own, which is just the amplitudes program, which we've heard a lot about throughout the course of the What is Particle Theory program. We have some amazing lectures on aspects of amplitudes. We're going to have another one this Friday afternoon on very modern developments. So I apologize for not being amplitudes focused in this talk, but this will hopefully occupy a good bit of time. And then, of course, the final thing that I want to focus on is generalized symmetries. And I know there are many of you in the audience who are far more expert in this than I, but what I really want to do is identify some opportunities for dialogue between the 2 programs, and I want to leave everyone with 3 questions, primarily facing the Generalized Symmetries program, that hopefully we can make progress in the coming month. Okay, so that's the plan, and I know what you're thinking. There's no way in heck Nathaniel's going to pull this off. So now we have another 40 minutes to see if I can. Okay, so to start with, let me just summarize a couple of open problems in particle theory. There are many of them, but just to give you a few, before we state the problems, of course, what is the thing that we are attempting to build on? In case you haven't thought about the standard model of particle physics, as I like to tell my graduate students, if someone shakes you awake in the middle of the night and says, tell me the standard model of particle physics, or else, you should be able to do this. So if, in case you're ever confronted with that, what is the standard model, right? It is a set of local symmetries. It is some matter, so we believe that there are 3 copies of sets of left-handed, well, what hand they are doesn't matter, but Weyl fermions. And Higgs boson, which is responsible for breaking this microscopic gauge symmetry down to the long-range symmetries that we see in everyday life. Okay, so it's a very simple-sounding hypothesis, right? But of course, it is rife, and it is dramatically successful across many decades of energy. But it is rife with open problems, and that's what charges a lot of activity in particle theory to this day. So one of the main open problems, of course, is what is the origin of mass? And you might say, well, the standard model tells us what the origin of mass is. The Higgs boson gets a vacuum expectation value. It breaks electroweak symmetry down to electromagnetism, and we're done. Okay. The actual state of affairs is much more complicated. So indeed, there is the phenomenon of electroweak symmetry breaking. The standard model as a hypothesis provides a perfectly reasonable explanation for it. But I want to emphasize that we actually don't know with any great confidence that that's what's happening. And we also don't know, in fact, we have deeper sort of meta questions like, even if that is what's happening, why is it happening at the scale that we observe? So again, we sort of believe that particle physics probably breaks down around 10 to the 18, 10 to the 19 gig electron volts. And we see the phenomenon of electroweak symmetry breaking happening here about 100 gig electron volts. And so there's a question of why this dramatic hierarchy of scales. In fact, we don't even know that it's just the Higgs of the standard model that's responsible for breaking electroweak symmetry down to electromagnetism. So that's why I've drawn I've only drawn the standard model symmetries sort of up here well above the TeV scale. It's completely reasonable that there be additional degrees of freedom that participate in electroweak symmetry breaking above the scale that we currently have access to, but within an order of magnitude that we will probe in the coming decades. And so we really don't know at what scale this microscopic symmetry of the standard model becomes a good symmetry. Good. There's, of course, when you say the origin of mass, I remember as an undergraduate, I got in trouble with Frank Wilczek because he was giving an SPS talk at Harvard, and he was like, he's going to talk about the origin of mass, and I was a very precocious young undergraduate, and I said, Professor Wilczek, isn't that the Higgs mechanism? And he reminded me that, of course, most of the mass that is around us is not due to electroweak symmetry breaking, it's due to the bound state energies of the strong interactions. And that's to say, even if we can write down the standard model at short distances, it also has a plethora of emergent phenomena that we don't understand fully, and that indeed have driven a lot of development in quantum field theory methods. So of course, the strong interactions go strong at a couple hundred MeV, and attempting to grapple with that has given rise to a lot of the methods that I'll discuss later in the talk. There's something that's connected, which of course is the origin of neutrino mass. We think, of course, that this has something to do with electroweak symmetry breaking, but the issue is in the standard model itself with the marginal and relevant operators you're allowed to write down, there's no source of neutrino mass. And so there must be some additional microscopic physics, and that microscopic physics, where that enters, could come down as low as the mass of the neutrinos themselves, but it could also come in at dramatically higher energies than we have experimental access to. Okay, so many, many open questions connected to the origin of mass, even though we've discovered the Higgs boson.
Related to this Higgs mechanism, my understanding is that there's a many choice of a Higgs field which may fit experiments. I wonder at the moment, how certain, how many choices still there, or maybe we pin down just one?
That's related to my statement that I don't want to confidently say that electroweak symmetry is restored above the 174 gigaelectron volts, which is what you would read off as the order parameter or the value of electroweak symmetry breaking. That's if we have a single Higgs boson. There could be multiple Higgs bosons. Their electroweak representations are somewhat controlled by the fact that the standard model has good approximate symmetries at low energy, something called custodial symmetry. I'll come back to that briefly later in the talk. But indeed, there are families of even weakly coupled models. Much more interesting, actually, is the idea that The Higgs itself maybe is an emergent degree of freedom from some strong dynamics that has a gauged, a global symmetry that's gauged by the standard model gauge group. And indeed, it wouldn't surprise you at all that many of these methods that have been developed to address questions in the strong interactions are also very helpful in giving us a more quantitative understanding of what that kind of physics might be. So that will be another theme of the talk. So indeed, the richness of possible explanations for electric symmetry breaking relative to this hypothesis is a real animator of what we're doing. Okay, the second one is the structure of flavor. Yeah.
What's the current balance of the neutrino mass?
The physical masses themselves. So of course we believe that well, it depends on what you mean, where the bounds come from. So it's possible that one neutrino is completely massless. The other neutrinos have to be at around 1/10 of an electron volt, right? We have constraints coming from, of course, the cosmological measurements of the sum of the neutrino masses. As you may know, I have a profitable side gig trying to reconcile cosmological tensions with other measurements for the neutrino masses. But we're in the sort of 1/10 of an electron volt range. But it's I mean, there's interesting cosmological tensions on the sum of neutrino masses, and then of course some inference we have from neutrino oscillation.
Yeah.
Okay. But so when I write neutrino mass here, I'm not saying that the active neutrino species we see are going to be this heavy. Rather, the additional microscopic physics that we'd have to add in order to explain neutrino mass could live up here. Yeah. And of course, there's been Majorana fermions are in the news a lot lately. We think that our Majorana fermions maybe live way up here. So we're not going to get in trouble anytime soon. But I think Microsoft beat us on that count.
So could the be at like some inflationary model scales as well?
Yes, so indeed, there are many more scales I could put also on here. So of course, physics of inflation. I'm going to set that aside from the current questions of today, but absolutely. But I think one good point of the program has been that people thinking about physics of inflation at these very high scales, there's also productive dialogue to have with people working through rest. Okay, structure of flavor, that is to say, we said the standard model fermions have 3 copies of these fermions. But they are arrayed sort of bizarrely, in energies down from, so the neutrinos, again, as we said, down here, the electron is at 511 keV, all the way up to, say, the top quark, which is living here close to 200 GeV, so orders of magnitude. And not just that they cover orders of magnitude in mass, but also that the patterns of mixings between them, between different generations, have interesting structure to them, which we have no ability to explain from the standard model itself, but instead we speculate that structure comes from somewhere else, and it can come from physics at shorter distances. So there's a range of physics scales over which new physics associated with the structure of flavor can emerge. Of course, there's the elephant in the room, is the nature of dark matter. I don't think we could fit an elephant in this room at this point. Nature of dark matter, which here I've drawn. Dark matter takes the cake in terms of covering all interesting scales, right? Candidates for dark matter can range all the way from, it's probably about, as we were discussing earlier, the current bounds are probably 10 to the minus 28 GeV, all the way up to the Planck scale, and then beyond if they're composite objects of more fundamental things. So of course, dark matter covers this entire range, and the ways you might look for it vary dramatically over this entire set of scales. So what it is, how it interacts with us, and how we discover it is a major question driving particle physics these days. Just 2 more. The violation or non-violation of CP. So famously, having 3 copies of fermions, generations in the standard model, allows for CP violation in their interactions. But what's bizarre is we've observed in some sense maximal CP violation in the electroweak interactions, but so far we have no evidence for CP violation in the strong interactions to the order of 1 part in 10. And it's puzzling to understand how it is that CP could be violated maximally in the weak interactions, but as far as we can tell so far, conserved in the strong interactions.
Can you define CP violation?
Right now, what I mean is there are terms in the Lagrangian which are not invariant under CP transformation. So a complex phase, which in this case cannot be removed by field redefinitions. So this is what we observe, for example, in the weak interactions. But the reason why it's puzzling, right, is that there can be phases in the Yukawa interactions for these fermions that in some sense the combination of the argument of the determinant of 2 types of Yukawa interactions appears to have no phase, whereas the combination of the argument of the determinant of the difference between 2 products of Yukawas does. So it's a very peculiar thing. It's not just that somehow there's a sharp line between the weak interactions and the strong interactions. There's basically these Yukawa couplings that give rise to fermion masses. One combination of phases is maximal, and the other, for no apparent reason, is very small. Okay, so that's an interesting puzzle. If you might try to explain it dynamically, there are actually ways to explain it across even larger scales than I've drawn. But of course, one of the most popular ways to do it is with what's known as the axion. And I just wanted to emphasize the axion because there are very interesting connections between axion physics and generalized symmetries. And the scale of global symmetry breaking that would give you an axion right now consistent with data sort of lies in the far UV. And then the final thing that I want to mention, again in the far UV, is unification. And that's just a statement that the charge assignments of standard model fermions with respect to this gauge group and the values of the standard model gauge couplings as we extrapolate them into the ultraviolet are all consistent with the idea that there's some unification of forces at some high scale. Not only that, of course, we believe ultimately there's some unification of this non-gravitational picture with quantum gravity, and so that would also be something that we fit into the umbrella of unification. And this is a sort of a deep and profound set of questions because it's physics happening at dramatically microscopic scales, but it's impressive that we can ever hope to find information about it from making measurements down at very low energies. And again, I think one of the lessons of the Generalized Symmetries program, as you apply it to particle physics, is there are a lot of interesting connections to taking the standard model as an EFT and relating it to physics coming from unification in the language of generalized symmetries. And this points to phenomena that, as particle theorists, we maybe sort of hadn't been paying much attention to for the last 40 years. Okay, so those are some of the open problems in particle physics. We're not going to solve any of them today, but what I want to do is illustrate now 3 opportunities where sort of non-perturbative methods that, again, have their genesis in the earliest days of understanding the strong interactions, but over time have developed to the point where they seem to be, as far as we've been able to figure out in the program, they seem to be very relevant to many of these other problems spanning dramatic range of scales. So I just want to give you a sense of 3 of those highlights. So the first one, highlight number 1, is lattice gauge theory. Again, lattice gauge theory has been around since the earliest days of strong interactions. As particle theorists, we are attentive to Wilson's formulation of lattice gauge theory in 1974. Of course, I know there are many other precedents in condensed matter physics. And the idea of Wilson was that we could productively study a Euclidean version of the strong interactions on a space-time lattice where charged fields live at points on the lattice and gauge fields as connections live as links. And even before doing a lattice field theory simulation in 1974, right, Wilson was able to use this picture to carry out at least an estimate in a strong coupling expansion of the potential between 2 static sources at large separation, and argue that it scaled linearly with the separation, which is in some sense an avatar of confinement. So even the simple picture itself, before you do calculations, gets you a lot of mileage. Then the remarkable thing has been from those early days, right, in the last 50 years, there's been dramatic progress in realistic lattice simulations of QCD, where now lattice simulations can include, the light quarks in the standard model with physical quark masses, which was something that was inconceivable in the 1970s, and can use it to make remarkable predictions for the strong interactions. And as a Euclidean simulation, it gives us things like the mass spectrum of bound states, form factors for the interactions of those bound states with other standard model particles. So that's a great success. That's something that's been going on continuously, of course, so that's not in any sense new. But what I wanted to highlight in the context of the program was some newer opportunities where the same methods now really stand to teach us a lot more than just about the strong interactions, but about possible solutions to all of these other problems. Okay, so the 3, again, things come in 3s, so I'll give you 3 lattice examples. Yeah?
Yeah, about this lattice gauge theory, I wonder what's the situation that can we put a full standard model on lattice?
Okay, so there's still, of course, an issue of chiral fermions, which we've heard about some interesting progress on. Well, a lattice person in the audience can tell me. I think it's fair to say we're not quite there, but impressive progress has been made. I want to give one example of something that is interesting on the march towards chiral fermions on the lattice. Of course, the reason this is a challenge is there's a famous tension between exact chiral symmetry and gauge symmetry, and this just manifests itself in lattice formulations of the theory. But there has been useful progress, and I'll mention one example in just a second. But just to give you 3 examples of really interesting progress for all of these other problems. One of them is actually scattering, and I'm delighted to see Steve Sharp is still here because he's the person to ask about this. So again, I think most of us who haven't worked on the lattice for years think, well, if we would like to get non-perturbative information about scattering processes, that's how we have learned most of this picture of the standard model is by scattering things off of each other. And that requires us to understand, field theory in Minkowski space-time with asymptotic states. And you would think when you take your field theory and you work in Euclidean signature in a finite lattice, you lose access to the scattering states. But, again, for all this time, there's been, starting with Lucier in the 80s, some methods for extracting, so really continuously from 86 onwards, methods for extracting at least 2 to 2 scattering amplitudes of bound states of the strong interactions coming from lattice data. And I think what's interesting, particularly in the context of this program, so that Lucier was 2 to 2, and what Steve has been telling us is that now we're really in a position to understand 3 to 3 scattering. And more broadly, you would hope in a program that is aimed at getting access to non-perturbative physics in scattering amplitudes, lattice calculations have a big role to play. And it's been very productive in the program to put these developments in interface with other developments coming from the S-matrix bootstrap or coming from Hamiltonian truncation. A second thing that I want to really emphasize, because I think this is something where we have a lot to gain, and is maybe very familiar already to condensed matter physicists, is the phenomenon of symmetric mass generation. Which again has, I think, long been familiar in the condensed matter context. It's also been familiar to four-dimensional theorists who think about supersymmetry. So we've had a phase of supersymmetric QCD that exhibits what we know as S-confinement, which we would say is akin to supersymmetric mass generation. The idea here is that you have no condensates that break chiral symmetry, but you can have some non-vanishing condensates that nonetheless gap the theory. And so this is something I think for a long time in 3+1 dimensions we thought was uniquely in the domain of supersymmetric theories and couldn't productively be extended to non-supersymmetric ones. But the really impressive thing just in the last couple of years has been especially driven by Anna's work is evidence that symmetric mass generation appears to occur in non-supersymmetric theories in 3+1 dimensions, in particular for SU3 with 8 flavors and SU2 with 4 flavors. And this is it's a beautiful phenomenon, of course, just for understanding the phase structure of non-supersymmetric gauge theories. So there's a lot to learn just about field theory from these lattice developments. But also as someone who thinks about generalizing the standard model, the ability to construct sectors that extend the standard model in which some phenomenon of symmetric mass generation occurs is remarkable. Because now you have the ability to contemplate adding chiral extensions of the standard model and nonetheless gapping them without somehow making them vector-like or coupling them to electric symmetry breaking. So in some sense, if we want, as we believe with greater and greater confidence that symmetric mass generation can be a feature of non-supersymmetric field theories in 3+1 dimensions, it really opens the door for a lot of interesting new developments. So I really want to highlight that. And we'll actually have a talk and a discussion on symmetric mass generation led by Anna, not next week, but the week after. The last point I just want to make, which is related to this, is just the ability, the growing ability and increasing number of results to answer questions about physics beyond the standard model in the lattice. So rather than just using lattice simulations to understand QCD, to understand Yang-Mills theory with varying numbers of colors and flavors. And where this connects to is a lot of different places. So for example, if you wanted to understand how the Higgs could emerge as an emergent degree of freedom from some other strong interactions, the spectrum of heavy resonances is something that you could study in specific theories on the lattice. It's also proven to be very relevant to thinking about theories of dark matter. So of course, dark matter could be lots of things. Something that is very interesting is dark matter could be bound states of some other strong interactions. And then what you would want to do is be able to compute the form factors of those baryons interacting with nuclei in direct detection experiments. That's essential to the interpretation of experimental results. And that's something, again, that we're now extracting from the lattice. So we'll hear a bit more about this from Ethan Neal in the program next week.
How about G-2?
What's really funny that you mentioned that. So I originally had 4 examples in the lattice, and I thought, keeping with my shamrock theme, I was going to drop G minus 2, but G minus 2 is another example of dramatic progress. And I would say that a great lesson to take, apart from its specific application, is we are now able to extract purely from the lattice hadronic contributions to precision observables. And one of the ways, in the next decade that we're going to continue to push up in energy here is with precision measurements of standard model symmetries, in which good, predictions for the hadronic contributions are important. So there's a bigger picture lesson there too. But it's funny that I meant to have 4 points here, but I figured it didn't fit on the shamrock. Okay, that's all I want to say about the lattice. I'm doing okay on time so far. So let me now turn to the second of these 3 opportunities. Yeah.
Yeah, since you mentioned symmetric mass generations, I wonder, there's a mirror fermion approach to this, to the first model, putting standard model on the lattice.
Yes.
Then using symmetric mass generation, since you can gap out the middle sector, then that's basically solve the.
Yes, this is another. Yeah, so exactly. So as I was going to say.
What's the situation?
Well, this is I don't know if on this here actually. Yeah. So what would you say?
There is a hope that it will work. I don't think anyone ever actually worked it out, but that's the eventual goal.
Okay.
Yeah, it's a beautiful possibility. Yeah, so for everyone else, the idea would be it's not that hard to put vector-like fermions on the lattice, and then if you could gap a chiral subset of them with symmetric mass generation, you would end up in the infrared with a set of chiral fermions. So that would be an interesting path to doing so. It sounds like.
So my understanding that one hopes to have a numerical calculation to demonstrate this actually work. Okay, thank you.
Yeah.
Yes.
Okay, good. That brings me, let me briefly sketch the second example, which is the S-matrix bootstrap. So again, this is something that even, this predates QCD. This really dates to the 1960s and our desire to somehow tame the zoo of hadronic resonances that appeared at the time. So, as many of you know, in the 1960s, Jeff Chu and others, the idea was to use bedrock principles of quantum field theory, so unitarity, causality, Lorentz invariance, to fully constrain the possible scattering amplitudes of the zoo of hadronic resonances, and in some sense uniquely fix the underlying theory. Now, since then, we've learned that that was, in some sense, an overly optimistic program, because now we know there's many, many large classes of interacting quantum field theories, each one of which gives rise to a consistent S-matrix consistent with those principles. And so it would be impossible to have a unique determination of the theory from those principles. But what we've had instead, really in the last decade, is a revival of this idea, recognizing now that in the zoo of quantum field theories in diverse dimensions, we can apply these same ideas to constrain the non-perturbative space of allowed scattering amplitudes. And so I think the revival of this really dates back to a paper by Paulos, Penedonis, Toledo, Van Rees, and Vera in 2016, but there's been a lot of related work since then and around the same time. And so the basic idea is to take analyticity, which is in some sense an avatar of causality. I'll say a little bit more about this in a second. Crossing symmetry, I'll say a little bit about more of all of these in a second. And unitarity, and use them to bound the space of allowed scattering amplitudes, and in potentially strongly interacting field theories. And the way this program plays out, just to make it slightly more concrete, of course, the scattering amplitudes are encoded in the S-matrix, which is a unitary operator. It has the non-interacting part where things just fly past each other, plus the interacting part. And if we just focus, for simplicity and for technical reasons, on 2-to-2 scattering, there's basically, we can parameterize the problem by the momentum dependence in 2 channels, which we parameterize with these the Mandelstam S and T parameters. They're just combinations of momenta that flow through the diagram in different directions. Then you can ask if you apply these constraints to the possible interacting part of the S matrix, can you then solve the constraints to define, in some sense, the bounded space of the amplitudes? And the way that this plays out, analyticity in 3+1 dimensions, we aren't able to prove things as well as we can, for example, about analyticity of scattering amplitudes in quantum mechanics. But it's a reasonable assumption right now that these obey what we call maximal analyticity, which is that these interacting parts of the scattering amplitudes are analytic functions of these Mandelstam variables, except for where there are physical objects, so poles that correspond to resonances and branch cuts that correspond to multi-particle production. crossing symmetry is the statement that actually scattering amplitudes in these different momentum channels are actually just boundary values of some common function. And so practically speaking, for the purposes of this kind of problem, it means there's relations between scattering amplitudes when the role of S and T are interchanged. And unitarity is, the implications, of course, of the conservation of probability. And in this case, the statement that the S matrix itself is unitary gives us a relation between the interacting part of the S matrix. And the reason that this is interesting is that if you then, for example, make a partial wave expansion of the interacting part of the S matrix, it gives you both a set of linear constraints and a set of nonlinear constraints. And if you can solve those constraints, for example, with semi-definite programming, then that is how you're able to leverage all of the power of these methods to define the allowed space numerically. But I should say, even the linear constraints that come from this are very interesting. So there's a whole program of positivity, which Brando Bellazzini has taught us a lot about during the program. And as we've come to say in the program, it's only S matrix bootstrap if it uses semi-definite programming. Otherwise, it's just sparkling positivity. Sorry, the dad joke. Okay, but the idea is you can apply all these things and bound the space of scattering amplitudes. And so what does it look like in the end? You could imagine Taylor expanding an amplitude in small momenta. So for example, you could imagine plotting it, say, in an order constant piece and an order S piece. And the result of these constraints is going to be some allowed region, where the space of perturbative amplitudes that most of us are accustomed to playing with is a small region sort of near the origin of the space. But in fact, everything, the broader set of non-perturbative possibilities is now constrained. And this isn't just saying what we can believe is true within the limits of our abilities. These bounds are now proven with both a primal method, which hypothesizes an amplitude and subjects all these constraints, so it finds amplitudes that satisfy the conditions, but also a dual method that actually rules out amplitudes on the exterior. And in many cases, these methods can meet. So we can uniquely determine the space of allowed scattering amplitudes.
Sorry, what's the two axes here?
Oh, here I'm just saying you could take your amplitude, okay, and you could imagine this 2-to-2 amplitude. You can imagine a Taylor expanding in a small momenta, and then you could plot, for example, what is the constant in momentum piece and say the order Mandelstam S piece, and you can plot some allowed region. So, particle theorists in the audience, you may say, why is this so great? If I don't know what's going on in this region, how do I make use of it? But actually, what's incredibly impressive about these methods, there's a number of things that are relevant directly to particle physics. One of them is that you really have the scattering amplitudes at the boundary of this allowed region, and so you can interrogate them for information about what is being exchanged. So in particular, now there's the ability to extract the spectrum of resonances, their masses and spins, for scattering amplitudes that live on the boundary. And that's, again, highly relevant to the question of what if electric symmetry breaking actually descends from some strong interactions in the ultraviolet. One way you could approach that at a quantitative level is you could consider the scattering, in some sense, if you turned off the standard model gauge couplings as being irrelevant to this problem. And you imagine the scalars that make up the Higgs boson emerge from some strong dynamics, you could simply study the allowed scattering amplitudes of those scalars. And that allowed region actually then allows you to engage in dialogue with, for example, precision Higgs measurements at the LHC. So the properties of the Higgs that we've seen can be added to these consistency conditions to shape the allowed region. And then you can ask questions about the spectrum of states at the boundary of the allowed region. And then you can go do searches at the LHC and other colliders for those states.
What does set the scale of the allowed region?
Good. So, there's a scale here, right, which is we fixed the masses of the external particles, which we're measuring at the light states.
Well, you assume the mass of external.
Yeah, so indeed. So for our purposes, for example, for studying this problem, that's a perfectly reasonable thing to do. So we're imagining we're studying the mass, the scattering of massive particles that are light compared to some heavy resonances. But that's exactly the sort of method you would like to use if you would like to understand what are the possible UV completions of electric symmetry breaking. Okay. Good. I should also say, something that some progress has actually been made during the program, and I appreciate the patience of all the S-matrix bootstrappers with me continuing to suggest this, but people working on it since then have made a bit of progress. This is also the kind of diagram that people who study dark matter interactions with the standard model draw a lot. In this diagram, they say, imagine we have two standard model particles and two dark matter particles. And depending on the direction in which you read time, this corresponds, for example, to scattering of dark matter off direct detection experiments at the Earth. It corresponds to production of dark matter in colliders, or it corresponds to annihilation of dark matter in the center of the galaxy. And we always sort of draw this picture as a cartoon. But there's actually a sense in which, subject to some assumptions, the S-matrix bootstrap can give meaningful content to what lives in the blob, what things can possibly live in the blob beyond what we currently parameterize. So there's also potentially interesting applications to dark matter. Yeah?
I also have a question about the S-matrix bootstrap.
Yeah.
Whether this automatically include non-perturbative instant effect, or whether you include instant or not include instant, you will have a different bootstrap or same bootstrap.
So all you're specifying are the low energy degrees of freedom. So I think it should include all of what you would call the instanton effects, right?
So you don't need to worry about it.
Alex can correct me if I'm being too optimistic here, but okay. I wanted to give one more example, and then I want to spend the last 15 minutes of my talk focused on the contact of generalized symmetries.
You could make one contact right there,
Yes.
right? Because these three principles, analyticity, crossing, and unitarity, if you have non-invariable symmetries, you have to relax them.
Yes, good. Indeed, yeah, crossing
One
particular.
plus one leads
Absolutely.
to integrable systems,
Yes.
but non-invariable symmetries are actually in conflict with these, so you have
Good.
to modify the
And so I'm not aware of the status of it, but indeed an interesting opportunity for progress is applications of the bootstrap where there's a relaxed version of crossing symmetry that instead the constraints consistent with the non-invariable symmetry is a great direction for further progress. Okay. Let me just briefly mention in the interest of time energy correlators. So I'll just give you the cartoon picture. So indeed, this is again something that dates back to the earliest days of QCD, and the basic idea is if at a collider, you imagine this is a projection of the detector, you're colliding particles at the center of your detector, and they're flying out, and you're measuring energy depositions in your calorimeter. A beautiful idea, which dated the earliest days of QCD, was to characterize this by asking about correlations between sort of detector observables that you can put at different positions on the celestial sphere. And you can simply look at, for example, correlations of energy deposited in these detector operators. And that's a really interesting probe of the theory. In particular, as you study these correlation functions as a function of angle, you're really probing the underlying microscopic theory in different regimes. Now, when this was proposed in the mid-70s, it eventually gave way, as we actually work at collider experiments, to other methods where we instead sort of cluster this radiation into objects that we call jets. We characterize the jets, and then we use them to do physics. But really, this has come back in particle physics really in the last few years, just because modern detectors actually have sufficient resolution to ask meaningful questions about these correlation functions at small angles, where you're starting to, in some sense, small angles correspond to low energies. And so you're actually able to, in some sense, image the QCD, the transition from low energy theory of free hadrons to the perturbative regime of QCD with one continuous variable. So it's incredibly powerful there, but also in the meantime, while we were busy working on jets at the LHC, the formal community applied these same ideas in this program of what's known as conformal collider physics. It turns out to be also an interesting probe of observables in conformal field theories. And so this has been dramatically developed outside of particle physics, but now, thanks to Evan and Ian and others, it's really re-entering. Not only is it something that gives us a lot of new understanding of QCD, but again, if you're thinking about extensions of the standard model that might address these problems, one of the cases that we sort of, for the most part, give up on having experimental access to is if some of the answers to these problems are contained in additional QCD-like sectors, where at the LHC, what you would see is other sprays of particles that basically look like QCD. And the question is always, well, how could you possibly pick those out of enormous QCD backgrounds? But if those sorts of additional sectors were there and you were occasionally producing those particles at the LHC, it is likely the case that our precision to make predictions for these energy correlators is the point where we could actually look for deviations from QCD behavior and use that to either discover or constrain new physics of that sort. So I think there's also really interesting applications for physics beyond QCD using these methods. Okay, so a little behind schedule, but I had enough time to say something about generalized symmetries. So let me turn to that, and then we'll wrap things up. Okay, so generalized symmetries, of course, the paradigm of generalized symmetries, I think, has been defined very sharply in the last decade or more. But generalized symmetries, in some sense, that paradigm is organizing pieces of information that were in field theories for a long time. Of course, we know that information about generalized symmetries, we had hints of it in condensed matter systems in the Ising model since the 40s. And there's a sense in which it also, like all the methods I've discussed earlier, in high energy physics, is connected in some sense to the advent of QCD. So when I started talking about the lattice, as a useful way to suggest confinement of the strong interactions, we said an avatar of that Wilson helped us to understand was that the potential between two static test sources at large separation, scaled like R, and the physical picture, of course, we have for that is if we have two static charges, there's some sort of confining flux tube that connects them. And this picture is good at all separations as long as there's not light charge, color charge degrees of freedom that can be pair produced in the vacuum to cut these flux tubes. So either this is true for arbitrary separation, or it's possible to pair produce color sources from the vacuum to cut these flux tubes. And of course, the latter is what happens in QCD. But in this latter situation, we can't really distinguish this phenomenon from simple Higgsing, whereas genuine confinement with these linear potentials at arbitrary separation, you might say, is a true measure of confinement phenomena. And already back in the 70s, we had a way of a criterion for understanding whether we had true confinement or we didn't, which is you could ask, do I have charged particles in my theory that are capable of cutting flux tubes? And that amounted to asking, if your gauge theory was SUN, you could ask, what were the matter representations of your theory? In particular, what were their charges under the center symmetry transformations? So the center, of course, is just the set of group elements that commutes with all the other ones, and you can take any irrep of SUN and decompose it into classes of the charge under the center symmetry. And so it turns out that only if you have sort of non-trivial anality or non-trivial charge under the center symmetry can your dynamical matter cut the flux tubes. Another criteria for that was if you had a lattice with a periodic time direction, you could construct, in some sense, an operator, which was the trace of a bunch of these links that went in the time direction, periodic in the time direction. This is known as the Polyakov loop. And the Polyakov loop transforms non-trivially under center symmetry transformation. So if the Polyakov loop had a vanishing expectation value, then there was true confinement. And it had non-vanishing expectation value, then the center symmetry is broken, and then you're back in this case. And the reason I say all of this historically, for particle physicists, what are we talking about? We're talking about a symmetry which acts on the extended objects, acts on the line operators. And this is why now we would say, in modern language of generalized symmetries, we think of center symmetry as being an example of a higher form symmetry, of a one-form symmetry, because the charged objects are these line operators. Okay, so of course, there's been a tremendous amount of activity in generalized symmetries in condensed matter, in quantum gravity, in mathematics. That's one of the reasons, of course, why we have this amazing program here in generalized symmetries at KITP. And we're at a stage where I think we're beginning to recognize the importance of generalized symmetries for particle physics, but I think there's a lot of room to grow and develop. And so really what I want to do just with the last 10 minutes is give you a couple of examples of things that we already know, and then I want to pose 3 questions really for the generalized symmetries community that hopefully we can use to set the stage for dialogue in the next month, in which we're all in overlap. So some of the things that sort of have been useful already, that we already know in the language of generalized symmetries for particle physics. One, of course, is the global structure of the standard model. So we actually had a nice talk by Adam Martin about this 2 weeks ago. We say, of course, the standard model gauge group is SU3 cross SU2 cross U1. But famously, we can take a quotient by a discrete group, which could be nothing, Z2, Z3, or Z6. And everything that we currently know in terms of the spectrum of charged particles in the standard model is consistent with Z6, but that can't rule out the other possibilities. And so in some sense, we don't even know what the standard model gauge group is, right? We think we're doing so well with the standard model, and we don't even know basic questions like what is the standard model gauge group. And of course, there's no local observables anyone can make by scattering particles that will tell us about this. But this controls, for example, the spectrum of line operators in the theory. It controls the spectrum of monopoles. And from a pragmatic particle physicist perspective, although we're not, hopefully we get lucky, we find a monopole, we put it in the lab, and we measure lots of things, and we figure this out. But even if we don't catch a monopole anytime soon, just by looking for additional particles charged under the standard model, depending on what their charges are, can help us refine the understanding of the global structure of the theory. So there's already, our sort of glaring ignorance about the standard model itself is made manifest in the language of generalized symmetries. Of course, something that has been incredibly powerful is the understanding of the relation between anomalies, both ABJ anomalies, which in modern language, Hotot and Shuhang and Yichol and Kantaro and Clay have taught us, ABJ anomalies in QED, we should actually think of the residual symmetry as being non-invertible symmetries. We also have learned from Thomas and from Clay and from Ken that even if it's not an ABJ anomaly, if there's just H'Tooft anomalies of global symmetries in the standard model, that they're what you would call a higher group structure. And these are all interesting because these symmetries are present in abundance in the standard model. So just a few examples. Of course, we know the axial anomaly of QED. Now we would say in modern language is an example of a non-invertible symmetry. And yeah.
So one experiment right now suggests Z6 rather than Z2, for example?
If you just look at the charges, so you can ask so of course, what is it saying? It says that the theory is invariant if I do a general gauge symmetry transformation under any of these, and then what am I allowed to mod out by? And so the question is, what other transformations can I do that would leave the theory invariant? And so it's a statement about the charges of standard model fermions, right? So what the current statement is the reason it could be Z6 is I can mod out by a center transformation of SU3, of SU2, and an appropriately chosen transformation of U1. But if I've had fermions charged in the standard model with different charges, I may no longer be able to pick the full set of U1 transformations. So that would change what you would say the global structure.
Those particles can be there, but they're very heavy, right?
Well, so they could be very heavy. So you have to get lucky, right? But it's an interesting. So this is something that Seth and Adam articulated in the paper last year. If you just ask what particles could you discover that would tell you about the global structure, it turns out that all the ones that would tell you that it's not Z6 carry fractional electromagnetic charges. And so then there's an experimental physics program that is interesting to pursue at the LHC and other experiments to really ask, do we have any low energy evidence for these particles? Now, it's a fishing expedition. You're not guaranteed to find, this could happen at scales that are inaccessible to us. But it's interesting that it is a motivation to look for things that you might not have otherwise been motivated for. But it's a good question to get access to. Yeah.
You can also get evidence the other way. In other words, unification into higher groups restricts these key evidence for unification like protons.
That's right. So depending on, the global structure is also determined if you embed the standard model in a simple group at short distances. And so the simplest unified theories that people like SU5 and SO10, they indeed predict the Z6. But other forms of unification that are in some sense less unified predict smaller n. And so, indeed, if you found evidence for a specific unified theory, that would also give you, or vice versa, if you saw something. Anyway, there's great. I think the thing to emphasize here is there's great interplay between infrared measurements and our understanding of what's happening at dramatically remote energies. Yeah.
You mentioned ISO 10. I wonder, from ISO 10 to 1, 2, 3 seems to have additional discrete group. Is that right? So when the additional discrete gauge group also sometimes kind of global structure, which should be also part of.
Yeah, I'm actually off the top of my head. I don't know what the additional global structure is from SO10 beyond the Z6, but absolutely. This is just to say. So a good point of contact between particle theory and the program of generalized symmetries is really this understanding of the global structure that particle theorists have historically not been attuned to, but is obviously very interesting. I just want to highlight here, in the interest of time, I want to leave you just with my 3 questions, so I can't go into these in detail. But one of the things we've learned, not only are these symmetries abundant in the standard model, and again, there's a really nice paper by Seth and Clay pointing out that these fermions in the standard model Q, U, D, L, E, they have a flavor symmetry and we turn off all the Yukawas, but those flavor symmetries actually participate in a higher group structure with hypercharge. And so that gives some very interesting implications about the possible UV completions of the theory. And I'd say, practically speaking, what these sort of things have reminded us of as particle theorists, which we're still exploring, is non-perturbative phenomena that, for the most part, many of us stopped thinking about in the 80s, with no good reason, that now we're returning to, recognizing that these symmetries give us a way to organize the information. So, for example, anytime you have a non-invertible symmetry, what it tells you, in the case of the axial anomaly, is that this global symmetry of the standard model is now tied up with the magnetic one-form symmetry of hypercharge. And one of the consequences of that, it reminds you, is that if you had a monopole carrying hypercharge, that symmetry, that global symmetry, would be violated in scattering off of the monopole. So this is just an example of monopole catalyzed violation of global symmetries. We've known about it since the 80s, but now we have a very precise way of mapping out when this occurs and how it occurs, and that has very interesting consequences for experiments. So for example, Lance, you asked in the discussion last Friday, do we have any predictions coming from generalized symmetries? And one of the things I pointed out was some types of unification, like trinification, they preserve some of these symmetries of the standard model, approximate symmetries like baryon number. But because of the anomaly, that tells you that actually that symmetry will be violated in scattering off of the unified monopoles of the theory. And that was something that we could have said and studied in the 80s, but we didn't. And the language of generalized symmetries now allows us to access it systematically. But maybe let me just end with my 3 questions. Good. So the first question is, I don't know how to, are there any new, so apart from, for example, non-invertible symmetries and these higher group symmetries, I want to ask, are there new or are there more generalized symmetries in 3+1 dimensions that are potentially relevant to particle physics? And the reason why this is really important, this is not, again, just a fishing expedition, is we've organized a lot of information by understanding the non-invertible and higher group symmetries of the standard model in particle physics. But you could have said all of that information because, for example, this has to do with anomalous global symmetries, and this has to do with similar phenomena. We could have said the physical consequences, we could have arrived at them without knowing this. So the question is, are there generalized symmetries that are not somehow related to things that we already knew about? Because that could teach us something dramatically new. Okay. And
just so,
yeah.
Does non-invertible symmetry really mean the ABJ anomaly?
Here, the example in 3+1 dimensions in Minkowski's, that's the thing that we, I guess that's yeah, so the question is, are there 3+1 dimensional non-invertible symmetries in asymptotically flat space-time that we could put to use? Yeah, that's the question. Good. The second one is, all of these generalized symmetries of the standard model, they are emergent symmetries, right? So the symmetries that we expect are probably not good symmetries in the far ultraviolet, but they become good symmetries as we go to the infrared. And well, as particle physicists, what we're accustomed to doing, particle physics is not the art of exact symmetries. It's the art of approximate and broken symmetries. We basically take selection rules of approximate and broken symmetries and use them to work out physical relations. And so the question is, because we don't believe these symmetries of the standard model are exact, we believe they're approximate, how can we fully map out the infrared consequences of their ultraviolet violation? So that question, you might say, is what is spurion analysis? So this is something that we've used very productively in the strong interactions. We know that the approximate global symmetries of the chiral Lagrangian are not exact in the ultraviolet, but we can follow them through the strong interactions going strong using, by promoting coupling constants to fields. This is what we mean by spurion analysis. And so the question is, what is spurion analysis for generalized symmetries, for higher form symmetries and non-invertible symmetries? Can we do a version of this, which of course has to be dramatically different, but can we use that to therefore parameterize the infrared effects?
Is this the same question as whether you can gauge non-invertible symmetry, or it is?
It's not obvious to me that it would, for example, I would just say, let's say that I know in the infrared I have an approximate electric one-form symmetry, but if I had charged particles at the gut scale, I would know that there should be exponentially small effects related to that breaking in the UV. And so the question is, how can I, in the IR, just knowing that I have an emergent one-form symmetry, and it's broken at some UV scale, how can I parameterize all the places where that breaking should appear?
Thank you.
Okay, that's what I would like to know.
But why are generalized symmetries necessarily emergent?
Well, they're not. They often are. It's just the examples. So for example, if I take the higher group, or the higher group, for example, structure of the standard model fermions, the ingredients of the higher group, in particular the magnetic one-form symmetry, is broken if I've unified the theory and I have dynamical monopoles. So it's only, the one-form symmetry is only good symmetry below the scale of unification. So, many of these ingredients are emergent in the IR, and we would like to parameterize the effects of breaking without necessarily committing to a specific UV theory. Okay, and the third one, so at the very beginning of the What is Particle Theory program, we start with a series of open questions. And my open question was what is the generalized Swift paradigm So what do I mean by that? Well, something that we've heard a lot in the language of generalized symmetries is the idea of a generalized Landau paradigm. If phases of matter are characterized by the symmetries they break, of course, for a period of time, we had apparent exceptions to this paradigm, and then it was discovered that those exceptions could be incorporated once you brought generalized symmetries into the game. So what do I mean by the generalized 't Hooft paradigm? Well, again, as Seth mentioned in the discussion on Friday, 't Hooft has taught us one way to understand small parameters in quantum field theories is if symmetries are restored when the parameters are taken to 0. And we have a lot of examples. Many of the puzzles of particle physics are apparent violations of this paradigm. So famously, the scale of electric symmetry breaking is a violation because the Higgs mass is dramatically lower than all the other scales in the theory, but there is no symmetry restored when the mass is taken to 0. And it's not just that we have exceptions in data, we also have exceptions in theory. So I can give you lots of examples afterwards about places where we think renormalization should connect operators, but when we actually compute the anomalous dimensions, they vanish. We have heuristic ways of explaining that right now. But for example, in 2 dimensions, similar phenomena are explained by non-invertible symmetries. So that really suggests that there are current mysteries, not just in data, but in theory in 3+1 dimensions, which don't seem to fit in the 't Hooft paradigm, but could be made to fit in the 't Hooft paradigm if we fully understood the generalized symmetries and how they entered into the story. So I think this is an amazing question, and if we can make progress on it, of course, that would be incredible. Well, that's it for me, so thanks very much for listening. I hope you got something useful out of it, and thanks for your time.
Other questions?
No, it's not really a question, but I was listening to this Codian analysis, was thinking about, say, this Dmitrievsky talk, where this monopole condensation, but not in the sense that they're real monopoles, but there is average which correspond to so-called monopole operator. And it makes connection to the symmetric possibility. So it could be kind of variants there which are not just associated with the real appearance of real.
Yes, absolutely. Yeah. So I mean, all of this represents progress with and hopefully I've emphasized control over things like symmetric mass generation, gapping without breaking chiral symmetries in any way has dramatic implications for how you try to address these problems. So any progress we can make would be great.
Right. So I have a question about Higgs boson.
Yeah.
So one question is that why Higgs boson has such small scale, right, composed at the UV?
Yes, assuming the presence of scales in the UV, of course.
Right. So I mean, this sounds very similar to, for example, there's a CFD in the background, and the Higgs boson is a composite operator of some more fundamental operator of the CFD, right? So that
Yeah, so that would be an explanation, and now it's an experimental question. And so this is why we like to make sharp theoretical predictions for where new degrees of freedom should appear in conjunction with that hypothesis. And that's why new strongly coupled methods help us to sharpen that. Right? Like at what point does a collider tell you that the Higgs is actually not a composite of some strong dynamics? To know that for sure, you'd have to be able to parameterize where the additional degrees of freedom should appear. How far can they be separated from the mass of the Higgs itself?
Yeah. Of course, one place that's interesting about your talk is the fact, one feature is that, in fact, you mentioned supersymmetry once, and not so long ago. That would have been, so I just wonder if you have some comment whether it could be still used as any kind of guide, obviously in certain kinds of simplifying situations, simplifying models and so forth. But do people thinking about beyond the standard model talk about supersymmetry?
So I mean, it absolutely has a role to play. I think the issue is that we were so strongly lampposted, for such a long time, and the dramatic impact of the LHC, results for supersymmetry. I think it was a productive eye-opening experience, right? Because you could end up in a very narrow pigeonhole when you had extreme confidence that you understood the microscopic theory of nature, and you could focus elaborate amounts of attention on that. And then when you discover that your confidence was misplaced, what it forces you to do is step back and look around And I think in some sense that's been driving in part a lot of the engagement of particle theorists here with, for example, the condensed matter community, generalized symmetries, recognizing that there's so many interesting things that we really had not been paying attention to, but we needed to because our confidence had been misplaced. Now, does supersymmetry still play a role? Absolutely. Supersymmetry at any scale is in some sense better than arbitrary fine-tuning of the weak scale, and so it is still a very useful experimental program at the LHC. Supersymmetry is also what we call a signal generator, so if you want to parameterize all possible topologies for new physics, supersymmetry does that. And then also there's, I think, a role to play in connection to some of this dialogue with new methods for strongly interacting physics, which is it is something that we did after the advent of cyber duality and our understanding of n equals 1 supersymmetric QCD. We understand the phase structure and duality in those theories, and you could ask now what happens to nearly supersymmetric gauge theories. We made some progress in that 20 years ago, and then we basically ran into a wall, which was that you can't be sure that there's not a phase transition as you take a nearly supersymmetric theory to a very non-supersymmetric theory. And so a natural question is, now that we have a lot more symmetries, right, can we revisit that question and get more control over the extrapolation to large supersymmetry breaking? Because if we could do that, then supersymmetry and our understanding of supersymmetric dualities would have an immense amount to say.
Exactly. I mean, sorry, just a quick follow-up. It was really that issue that interests me, the fact that we're in danger of sort of running off in the other direction, and actually maybe we just went too far with supersymmetry, but actually some of this other stuff can
Exactly. And I think now is a good time. And of course, everything is cyclic with 20-year periods in physics, but that's great, because indeed, this is a point we should come back to.
So related to the three questions that's on the Blackboard, I think another question we can ask is, let's look back. Like in particle physics, what is Lie group good for? Right. So I mean, it's good for many things, but one thing that it's good for is that for every Lie group, there's a Yang-Mills theory, and there's a new quantum field theory that's labeled by the Lie group. Now, is there something for the generalized global symmetry, especially for continuous non-invertible symmetries? Can we build new quantum field theory out of these symmetries in the spirit of Yang and Mills? And maybe that would be. I think the most trivial case is if you consider some Yang-Mills theory with disconnected gauge group, you can view them as a gauge theory of non-invertible symmetry. Does that buy us new insight? It's not super interesting because we also know how to think about it in terms of ordinary group. There are some theories that we cannot think about it this way.
Right. But you have to start somewhere, and that's my feeling. The examples that we have so far, also just generally of non-invertible symmetries and Peopleson mentioned, they might seem not incredibly powerful because they're related to things we already knew, but you have to start somewhere. And my sense is that we will only get more and more interesting. And the moment you have any sort of new set of theories, of course, I can promise you that particle physicists thinking across this range of scales will figure out how to put it to use. So, absolutely.
Thank you for that.